In this video, we solve problem 15.2.010 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition, We're asked to consider the following. C is a path. It's a line segment starting at 0, 0, and ending at the point x equals 2, y equals 4. And I'll start by sketching that. We go from 0, 0 to x equals 2, y equals 4. Okay. And in A, we're asked to find a parameterization of the path C, given R of t, and then we have this big blank box where we're supposed to type our answer. And then we're also told that t is supposed to range from 0 to 2. And then once we find that parameterization, we will use that to evaluate the line integral over C. Okay, so for the first part, you notice we're dealing with a line segment in the plane. So that means our vector valued function R of t will have an x component and a y component. And I know that I want my t values to range from 0 to 2. Now, I also notice that as we travel along this line segment, our x values range from 0 to 2. So I think what I'll do is I'll just let my x equal t. And that will work because when t equals 0, x will equal 0. And then when t equals 2, x will equal 2. And that'll be fine as long as our y of t and our x of t satisfy the equation of this line. And so what we'll do next is we will find the equation of the line in rectangular coordinates, just in terms of x and y. We know that that's just y equals mx plus b. Now the y-intercept will be 0 because our line crosses the y-axis at the origin. And we start here and we go up 4 and over 2. So rise over run is 4 over 2. We multiply that by x. So y turns out to be 2x. So that tells us that no matter what x is, y is twice that. Well, if x is equal to t, then y would be 2 times t. You can write it like that. I prefer that myself, that's component form, or you can write it in terms of standard unit vectors I hat and j hat, that's fine too. Okay, now for the next part, we're asked to evaluate the line integral over C of this function of 2 variables x and y. Now before I talk about that specific line integral, let's talk about evaluating a line integral of a function of 2 variables, a scalar function of 2 variables like this. Now we've got a lot of variables here. This says you're going to take the values of this function f of x and y, and you're going to multiply them by a tiny arc length. Then you're going to add all of those together as you travel along the curve C. Now we need a variable to tie all of these together. The variable that we use to tie all of those together, is the variable t. So we're going to say this line integral is the same as this line integral. We'll evaluate the line integral from t equals a to t equals b, where t equals a and t equals b correspond to our initial point on the path and our final point on the path. So we could think of a particle maybe traveling along this path and at time t equals 0 being here and at time t equals 2 being here. So as t goes from 0 to 2, we travel along the whole path, we traverse that whole path. So that means this is our a value and that is our b value in this particular case. Now, we also need to know what f is in terms of t, which is actually really easy to compute. We know what x is in terms of t when we're on that path, it's given by t, and we know what y is in terms of t when we're on that path, it's given by 2t. In general, I would substitute in those equations for x and y of t here, and now my integrand is written in terms of t, or my original integrand is. Now remember, ds is a tiny length. That tiny length turns out to be the magnitude of r prime of t times dt. If you're thinking about as a little distance traveled, this just says that the distance, little tiny distance traveled should be your speed times a little time increment. So this is how we will evaluate this. Basically, we need a ds in terms of t, we need f in terms of t, and then we need the bounds. The bounds are really easy. So I guess we just need to focus on that f in terms of t and our r prime of t, or or excuse me, our ds in terms of t. So I've got f of x and y. In our case, we're asked to evaluate the line integral of x squared plus y squared over this curve C, or this path C. So f of x and y is x squared plus y squared, but we want that in terms of t. So we're going to replace x with x of t and y with y of t. Now x of t turns out to be t, and y of t turned out to be 2t, given the particular parameterization we came up with. So I've got t squared plus, you got a product squared, you want to square each of the factors separately. T squared plus 4t squared is 5t squared. And that is our integrand in terms of t. The original integrand in terms of t. Not too bad at all. It's just a 5t squared, nice and easy. Now, we also need to multiply by the magnitude of r prime of t. Times dt, that is our ds. We want ds in terms of t. So first I'll write down r prime, or excuse me, r of t. R of t was a vector with components t and 2t. Just take its derivative, component by component. I get 1 and 2. And then I'll find the magnitude of that. Remember, whenever you're taking the magnitude of a vector, you take the components, you square them and add them and take the square root. This time we don't have functions of t, so it's really nice. We just end up with the square root of 5. So that means our ds is that magnitude times dt, which just happens to be a square root of 5 times dt. Okay, that's nice and easy. Now we just substitute everything on up here and we evaluate that. So we had the line integral over c of x squared plus y squared ds. Turns out to be the line integral, or excuse me, the sort of calculus 1 integral from t equals a to t equals b. A is 0, b is 2, because that's where we start and that's where we stop. We're tracing this out from t equals 0 to t equals 2. Then our x squared plus y squared turned out to be 5t squared in terms of t. And ds gets replaced by square root of 5 times dt. 5 square roots of 5 is a constant, so I'll write that down. Then I'll take the antiderivative of t squared with respect to t. So I'll add 1 to the exponent, divide by the new exponent, evaluate from t equals 0 to t equals 2, and subtract. When we plug in t equals 2 here, we're going to get 8. So if 8 times 5 root 5 is going to be 40 root 5. And take all of that and divide by 3. When we evaluate at t equals 0, we get 0. So that is the value of the line integral over that path. Let me know if you have any questions.